And we're doing an updated video today on the new and improved version 2 power mole, thinner, longer range, and stronger. Okay, so from an antenna perspective, the wireless charging or inductive charging is really just sending power through a coil like a transformer, except it's an air gap transformer. And so we have some ferrite that's in there to shield the electronics so that the magnetic fields, we kind of want them to go out from the product, so to be maintained within the gap. And so this ferrite material, which is high permeability but low conductivity, helps with that. And we use Litz wire, which is a wire that's made up of a bunch of really thin strands of wire, and that helps increase the inductance faster than the resistance, and you get a higher Q or energy transfer efficiency as a result. So we choose a resonant frequency here, 300-400 kilohertz, and we match it to that frequency with capacitors, and so just put a square voltage across it. And that's pretty much an inductive charger. On the receiver side, you rectify it and drop it down to 5 volts. So here, a little test setup, we're delivering 5 watts on the output. So we have an electronic load here that's absorbing power from the receiver, so that's constantly taking 5 watts. And we have the transmitter over here, which is connected to this, which is just constantly pulling power, and it's going through the gap. So what happens if I put my hand in there? Will the magnetic fields be affected at all by that? And so I can put my hand in there. I don't feel anything, first, and second, I'm not seeing any change in the input power. So I put my whole hand in there. There's some flicker to the input power for some processing, but I can't feel anything, and nothing changes on the input power. Okay, so let's see. So wood, let's see, no change. So again, there's no properties in the wood that really affect magnetic fields. We can take water, put some water in a baggie. So this is very high permittivity, about 80. Put it in there. Magnetic fields don't care. So no change. So it's kind of cool. Drywall, nothing. So glass, wood, plastic, ceramic, whatever. It doesn't notice it. So then you say, okay, what about metal? So you'll see what happens right away. So here's an aluminum can I smashed. So if I start putting that there, you see the power immediately start changing. I'm not putting it all the way in. The magnet, so we'll see input and output power. So you start to see a lot of output power. You see we're not delivering the power anymore. So the system will notice like, hey, something's getting screwed up, it'll shut down. But yeah, so metals, right away you can see like huge input power change, and the system shuts down. That's safety mechanisms. So pretty cool. You can kind of see like what matters, what doesn't. System booted back up now that everything's okay. Another interesting material is ferrite. This is a super high permeability, low conductivity. So that's what makes up the shielding materials. So if I put it in between, power drops, we've shielded the magnetic field, and it stops, comes back on. So this prevents power from transferring. Something that's cool is like, what if I put it on the side like this? So here, I'm still delivering power, and the efficiency went up, so the input current goes down. So this is actually helping the power transfer. So the magnetic fields are kind of going through that superhighway of permeability. Magnetic fields can kind of skip right through like a transformer. So that's actually kind of cool. But again, if you put it between, it'll shield. So metals will affect it. Your hand, nothing. Can't feel it. No change in input output power. Wood, all that stuff, it's the same. So pretty cool. So yeah, pretty cool demonstration of what's going on with magnetic fields in between here, and hopefully you learn a little bit about antennas and electric and magnetic fields as a result. Thank you.